In the last section, we looked at the idea of Riemann sums and how the more and more rectangles we used, the closer we got to the actual area under the curve. Today, we expand that concept into the idea of a definite integral and the fundamental theorem of calculus. When we take those Riemann integrals and get an infinite number of them, we can define this as the idea of a definite integral from a to b, which gives us the actual area under the curve as opposed to an estimate based on the Riemann sums. And this allows us then to restate the fundamental theorem of calculus that we used last time, in that if f of x is a continuous function on an interval ab, then the antiderivative can be used to calculate that definite integral, or the area under the curve. Let's do some examples using our rules of integration that we already know. For example, here, if we wish to calculate this definite integral, the integral of 2x is 2x squared over 2, which simplifies to x squared, and then we're going to evaluate it from 1 to 2. Using the fundamental theorem of calculus, this means we're going to do 2 squared, we're plugging in that value, minus 1 squared, which gives us 4 minus 1, which is 3. In this example, we can rewrite our function as x to the negative 1/2 dx. And using our rules of integration, this gives us x to the positive 1/2 over 1/2, which we can reciprocate that fraction to give us 2x to the 1/2 from 1 to 4. Plugging in our values there, we end up with 2 times 4 to the 1/2 minus 2 times 1 to the 1/2, or 2 times 2 minus 2, which is 2. Last but not least, in this example, if we look at the definite integral of e to the x, the integral of e to the x is e to the x from 0 to 1. Plugging in 1, we have e to the first minus e to the 0, which gives us e to the 1 minus 1. We have some additional properties here of definite integrals. Note in this property, we're going from a to a, which essentially means we're covering no area on the x-axis or no span on the x-axis. And in that case, the area under the curve would be 0. These two should look familiar. We're adding and or subtracting or multiplying by a constant, which we can do on indefinite integrals. And now we're showing that can be expanded to definite integrals as well. Let's see how those apply in the examples shown here. If I'm going to calculate the derivative here, I'm going to take the integral of each portion, which is going to give me x cubed over 3 plus the ln of x for this portion minus 3 e to the x. And then we're going to evaluate that from 1 to 2. When I plug in those values, I get 2 cubed over 3 plus the ln of 2 minus 3 e squared. And then I'm going to subtract the entirety of 1 cubed over 3 plus the ln of 1 minus 3e to the first. Simplifying, we get 8/3 plus the ln of 2 minus 3e squared. Note this goes to 0, and we are left with minus 1/3 plus 3e, which results in 7/3 plus the ln of 2 minus 3e squared plus 3e. In this example, we are going to have to use u substitution. Remember, we're going to choose our u to be based on the higher powered function, which gives us u is x squared plus 1, resulting in du is equal to 2x dx. We see here we're missing a 2, so if we multiply by 2 on the inside, we multiply by 1/2 on the outside, which gives us 1/2 u to the 1/2 du. All of this combines to give us du. We can no longer use 0 to 1 as our upper and lower values on the integral. We have to now calculate those. When x is 0, that means u is going to be 0 squared plus 1, or 1. And when x is 1, that means u is going to be 1 squared plus 1, or 2. We integrate the same way now, and we have u to the 3/2 over 3/2, and we still have that 1/2 out front. which is going to give us u to the 3/2 over 3 from 1 to 2. Upon plugging in those values, note the 2 to the 3/2 is going to give us a square root of 2 cubed. And when we simplify, we are going to end up with 2 square roots of 2 over 3 minus 1/3. The last portion to point out here is the average value of a function. Notice if we want to determine the average value across a range of a function from a to b, we're still going to take that definite integral, but then we are going to multiply by 1 over b minus a. Much like in the average, we do the total divided by the number of items. Here we're doing essentially the same thing. Using this first example, we want the average value of 8x minus x squared on 0 to 8. Using our formula, we're going to do 1 over 8 minus 0 from 0 to 8 of the function 8x minus x squared dx, which leaves us with 1 over 8 times 8x squared over 2, which is 4x squared minus x cubed over 3. When we plug in our values from 0 to 8, we are left with 4 times 8 squared minus 8 cubed over 3 minus, notice each of those values will be 0 when we plug in 0. And performing our operations there, we're left with a value of 10.6. On a practical side, this can be used to find average sales. So for example, here we have a company that is selling 1/2 t squared plus t speakers per month, where t is the number of months. To determine the average during the first 6 months, we're going to do 1 over 6 minus 0 from 0 to 6 of 1/2 t squared plus t dt. Performing our integration, we get 1/6, and then we have t cubed over 6 because we had 1/2 and then the 3 that results from the integration plus t squared over 2, again from 0 to 6. Notice when we plug in the 0, that portion is going to disappear, leaving us with 1/6 times 6 cubed over 3 plus 6 squared over 2, or a final value of 1/6 times 36 plus 18, which when you calculate that out gives a value of 9. Since this tells us it's in hundreds of speakers, it would be 900 speakers is the average sales for the first 6 months.